This is going to blow your mind. The secrets of the universe are hidden in light we can't even see. So what is a blackbody's spectrum? Imagine a metal rod. Heat it up and it glows red. Make it hotter and it turns white. This glowing is the blackbody spectrum in action. A blackbody absorbs all incoming light and radiates energy based solely on its temperature. As it gets hotter, it emits more radiation at shorter wavelengths. This concept, explained by Planck's law, helps scientists determine the temperature of everything from a heated rod to distant stars. By studying blackbody spectra, we've confirmed the Big Bang theory and developed infrared cameras. So next time you see a glowing object, remember, it's not just bright, it's revealing the secrets of the universe.
A blackbody is an idealized object that absorbs all incoming electromagnetic radiation, light, heat, or any other wavelength, without reflecting or transmitting any of it. A blackbody does not stay dark. Instead, it emits radiation depending only on its temperature. This emitted radiation is called blackbody radiation, or the blackbody spectrum. The blackbody spectrum shows how the energy emitted by the object is distributed across different wavelengths. The temperature determines the type and intensity of the emitted light. Blackbody spectra are key to understanding heat radiation in stars, planets, and the early universe. The sun behaves like a near-perfect blackbody, emitting radiation across the visible spectrum, peaking at yellow-white light because of its temperature. A blackbody is like a glowing stove burner. It absorbs all incoming heat and light, but radiates energy outward as it heats up. All objects emit thermal radiation if their temperature is above absolute zero. This radiation arises from the random motion and vibration of atoms and molecules inside the object. The faster the motion at higher temperatures, the more energetic the emitted radiation becomes, shifting it to shorter wavelengths. Cool objects emit infrared light, which we feel as heat but cannot see, while very hot objects like stars emit visible light or even ultraviolet light. A heated metal rod glows red at first, then white as its temperature increases, shifting the light to shorter and more energetic wavelengths. Thermal radiation is like boiling water. Cooler water releases faint steam with longer wavelengths, while hotter water produces fast-rising intense steam with shorter wavelengths. As an object heats up, the color of the light it emits changes. Cooler objects glow red because they emit lower energy, longer wavelength light. As the temperature rises, the object emits more energetic, shorter wavelength light, shifting to orange, yellow, white, or even blue. This phenomenon explains why cooler stars appear reddish, while hotter stars shine blue or white. Temperature directly determines the color of emitted blackbody radiation. A campfire's embers glow red because they are cooler, but the blue part of the flame is much hotter and emits shorter wavelength light. Changing temperature is like tuning a radio to different frequencies. Hotter objects broadcast on higher energy channels, making their glow brighter and bluer. The peak wavelength of blackbody radiation, the wavelength at which the most energy is emitted, shifts with temperature. Hotter objects emit more radiation at shorter wavelengths, while cooler objects emit at longer wavelengths. This relationship helps scientists estimate the temperature of distant objects based on their emitted light. The sun's peak radiation is in the visible range, which is why it appears white or yellow. Cooler stars emit primarily red light, while hotter stars shift to blue. The cosmic microwave background radiation peaks in the microwave range, corresponding to a very cold temperature of about 2.7 degrees above absolute zero. Peak wavelength is like the loudest note in a song. Its position changes depending on how hot the instrument object is. The total energy radiated by a blackbody increases dramatically as its temperature rises. Hotter objects emit much more energy per unit area than cooler ones, which is why stars are so luminous compared to planets. Even a small increase in temperature causes a large increase in the total energy emitted. This is why very hot stars can outshine much larger but cooler objects. A star twice as hot as another emits many times more energy, which is why blue stars appear much brighter than red stars. The total energy emitted by a blackbody is like the power output of a furnace. It grows exponentially as the temperature increases. Blackbody spectra are critical in astronomy for determining the temperature, size, and energy output of stars, planets, and galaxies. By analyzing the light emitted, scientists can estimate how hot a star is and even determine its age and composition. Most stars emit light that closely matches blackbody spectra. Cooler stars appear red, while hotter stars appear blue or white, providing a way to classify stars based on their temperature. The sun's temperature of about 5,800 degrees Kelvin produces a spectrum peaking in visible light, which is why daylight appears white. Blackbody radiation is like a cosmic thermometer that lets astronomers measure the heat of distant objects by analyzing their light. The cosmic microwave background, CMB, is the faint glow of radiation left over from the Big Bang, exhibiting a nearly perfect blackbody spectrum. This radiation provides crucial evidence for the early universe, showing that it was once extremely hot and has been cooling as the universe expands. The temperature of the CMB is about 2.73 Kelvin, and its radiation peaks in the microwave range. This discovery confirmed key predictions of the Big Bang theory. Satellites like COBE and Planck have measured the CMB, revealing it to be the most precise example of a blackbody spectrum in nature. The cosmic microwave background is like a faint glow from the universe's fireplace, still radiating light from the dawn of time. Blackbody radiation explains many everyday phenomena, from the glow of a red-hot stove to the operation of incandescent light bulbs. It forms the basis for technologies like infrared cameras, which detect the heat emitted by objects, and thermal imaging used in medicine and engineering. Infrared radiation emitted by blackbodies is invisible to the human eye, but can be detected by specialized cameras to identify temperature variations. Infrared cameras are used to detect heat loss in buildings, diagnose injuries, and help firefighters locate people in smoke-filled areas. The study of blackbody spectra has been fundamental to the development of modern physics, including quantum mechanics and cosmology. It explains how energy is emitted by stars, planets, and galaxies, and provides evidence for theories like the Big Bang. Blackbody radiation also helps scientists design efficient energy systems, solar panels, and sensors. Blackbody spectra are like a universal blueprint for energy emission, helping scientists decode the physical world, from the glow of stars to the origins of the universe.